This is my Evil Claw robot, and it's a one of a kind. You can't buy this, you can only build one yourself. It's the most important step towards giving myself actual working robot arms. And it took 6 months to build. Because I didn't want some simple claw grabby thing that fell out of a cereal box. I wanted something that looks like magic. Check out how smoothly it spins the globe. The fingers move exactly where I tell them to, within 2 millimeters. They're coordinated. It's actually better than real fingers. And it makes me look like I want to take over the world. My own Evil Claw robot. But God, it sucked. It took weeks of trying to stop it from freaking out, redesigning the same part 5 times because it kept ripping itself apart, relearning high school maths, and then finally getting the fingers to work together. This might seem like a lot of effort just to have an Evil Claw robot on my desk, but it's the first step into turning myself into Doc Ock. Oh wait, no. It's going in the wrong direction. There we go. To build this claw, I'm going to start with a design that already works well and is real. A robot called Axis. Wow, projectors are bright. This is stupid. These are my 3D printed titanium sunglasses. Check out this link if you want a 3D print you're on. This is Mark Zatrakian. And Zatrakian's from the fucking future. Mark Zatrakian is a robotics expert. He has a robotics company and he's even competed in Robot Wars. He built Axis as a robot to rotate a globe, showing that robots can have fine-tuned dexterity and that robots can be art itself. I'll be mixing Axis with the art from Doc Ock, plus some of my own style to make something a bit more original for my own build. What are you looking at? Now, Mark uses 5 fingers to rotate his globe, whereas we really only need 3 points of contact to hold up an object like this, and a 4th finger to rotate it. So that means only 4 fingers instead of 5. You would think that makes things easier. So that means I need to model up 4 fingers, 12 servos, the electronics to control it all, and a base to mount everything together. Speaking of servos, the one Mark uses are the MX106 from Robotis. Yes, I'm in the closet, don't question it. They're industrial grade and not meant for hobbyists, so they're made with metal gears and put out almost 10 Newton meters of torque, or 100 kilograms per centimeter. For comparison, most hobby servos put out between 12 and 25 kilograms per centimeter. They also combine the DC motor, controller, driver, sensor, reduction gear, and network all in one tiny package. But there's one major problem. They cost almost 1,000 Australian dollars each. Wait, does that mean that Axis cost at least $12,000 in parts alone? What the fuck? I can't afford that, so I'm going to use the XL430 instead. They're also made by Dynamixel and are part of their low cost range. They have most of the same features, but are weaker, made of plastic, and most importantly, only $85 each.
What the fuck are you
I said not to question! So now that I've got my servos chosen, let's sort out the dimensions. I want each finger to be able to touch each other at the very top, to match this look from Doc Ock. Future Omar here. If there's anything I regret about this project, it's the decision I just made here. I don't need the fingertips to touch at the top, but now that they do, it causes so many other problems. Whatever, I'll explain at the end, you'll see what happens. I also wanted a little space in the middle to allow for electronics and the limited cabling. To round things out, this length will total 100 millimeters, and using some trigonometry, I can figure out the rest of the dimensions. Each link needs to be precisely 142.69
nice
millimeters. Let's get to designing in Fusion. There won't be much weight at the top, so simple links the same size as the servos should do. The servos themselves will be the weak points anyways. But I do want to add some Doc Ock style shielding to the outside, so I'll add some mounting holes for later. 3D print it out, put it together, and now we got a finger. By the way, if you want to build this robot yourself, all the STL files, the full codebase in both Python and Arduino, and the full parts list is available on my Patreon. So I guess this means that this video is sponsored by my Patreon. I'll also be sharing behind the scenes videos, taking in ideas, and chatting a lot more there, so links in the description below. And if you like what you see so far and want to see more, subscribe for robots. Okay, now we got a finger. Time to move it. I've connected a testing board so I can set up each servo with an ID and then link them all together in a chain. I can control each of them individually using this app, but I need to create a program from scratch to control them all together. I'll cut up something in Python since Dynamixel have the documents to support it. Okay, 3, 2, 1. Now I can move each servo manually using this all-in-one window. Sweet.
oh fuck
Okay, I forgot to include restrictions because obviously you can't twist all the way around.
Servos can easily break, so you need to put code in to prevent it from breaking itself. But this only controls the servo angles, and the tip ends up wherever it ends up. You can calculate where this endpoint is in the world. This is called forward kinematics. But I need the opposite to happen, where I just tell it where the tip needs to be, and it figures out the rest of the angles for me. This is called inverse kinematics. Inverse kinematics works by taking in where you want to be in the world using an XYZ axis and spits out the angles that each servo should be at. To calculate this means using trigonometry, a bunch of matrices, and other math stuff I hate. Luckily, I found this Python library called the Robotics Toolbox for Python. This library was created by actual researchers within the field of robotics, so you know it's serious business. I have no idea if I'm underutilizing it. I assume so because I barely understand some of the stuff they reference, but hey, it works for me. Would this count as a citation for their work? Huh, I guess not. Sorry guys. Link in the description below if you want to use it yourself. Install it, configure your robot and code, call its inverse kinematics function, and done. You have the robot moving to exactly where you want in space. And look at this. It's working great and it's moving so well. Oh. Inverse kinematics is pretty awesome, but this is what happens if you tell it to try and reach a point that the robot physically cannot reach. It's called the singularity. It's around this time where I found out how fragile certain parts of my robot are, so I had to beef up a few links. As for the singularity, we've fixed that the same way as everything else we've been fixing so far. A little more code. By the way, we're still not done yet. There's still other stuff we need to solve for. If we go from one point to another, the servos will move to their new positions quickly. But in most cases, the tip won't move in a straight line, as the motors will all move as fast as they can to their new angles. Some will only need to twist a short distance. We need to plan each movement and create a series of positions with timings locked in. This is called path tracking. Since we're rotating a globe, we want the points to follow a circle. This means for each finger, we need to plot the movement points in an arc. This is the shape that will allow the robot to twist in a circle. In this case, we'll have each finger move just under 1/3 of the way around. To be absolutely certain of where the tip is, we'll first ask each servo what angle they're at. Then we'll use forward kinematics to derive where the tip is in space. Then we'll map out the arc along the XYZ axis. But once we get to the end, we need to get the tip back to the starting point without dragging the tip against the globe. So we repeat the action in the opposite direction, but with an offset in the x-axis, away from the globe. Also, with 4 fingers, we need this reverse action to take 3 times faster than the normal movement. Add in a smoothing effect so the tip doesn't shake all over the place, and we've got 1 finger sorted. Time to sort out the rest. Now that we have 4 fingers, I'll need a new board to control them all. This is the Open RB150 and it has 4 ports, 1 for each finger. The coding should be easy. I'll make all 4 fingers do the same movement using the same code. I'll offset each finger by 1/4 of the cycle, so there's always 3 fingers in contact with the sphere and a 4th is moving back. I even expanded the software so I can easily control all the motion parameters and PID settings for the servos. It's still running on Python, but it's all controlled by this website, so I can see what it should be doing. It can even be remotely controlled. But there's one last thing to get right, and that's the exact specifications of the globe. Wait. Do I have to measure the exact diameter of this globe and then figure out exactly which latitude I'm going to stick the claws on? Nah, stuff that. We're going to make this guy dynamic. What I mean to say is that there'll be inputs and outputs. And actually, you know what I don't want to deal with anymore? A computer that's connected to it all the time. So let's just do a massive software migration from Python to C++ so that I'm running everything from this little board. Moving it all here means I can use potentiometers, otherwise known as knobs, on the side of the robot. Want to make it higher? Turn this knob. Want to make it go faster or reverse the direction? Turn that knob. Knobs for everything. Actually no, just 4 knobs, thanks. Using these knobs instead of the computer means I don't have to be specific. I just have to adjust the parameters I programmed in, and eventually it'll be good enough. Enough about knobs. Another side effect of converting all the code to C++ is that I'm no longer using the robotics toolbox for Python anymore. Sorry guys, your work is no longer being used. Anyways, are we done? Nah. There's one last critical thing that we need to take care of. Making it look sick. I've designed the outside shield layers and the base to reflect the nature of this robot. I grew up playing Halo, so I'm borrowing a few design elements from there. Plus of course Doc Ock from the Spider-Man movies. Just like his claws, these shields will act like armor to protect the sensitive insides. I also designed in these LED filaments, partially because I wanted a reason to play with LED filaments, but also because it looks amazing lit up on my desk in red. I went through a couple of iterations and broke a few filaments along the way, but at this point I just want the project to be done. Keep in mind these LEDs and shielding are important, but also I'm not letting the idea of perfection ruin good enough. With all that finished, it's time to see its final form. Remember how I said there's a problem with the fingers? Now that it's fully finished, let's see what it could have done better. First, the geometry looks off compared to Doc Ock's claws. There's a gap at the bottom here that if I closed up with the shields, it would look comical when it was open and it would probably collide with each other. Second, the length of the links means that every little mistake or inaccuracy results in a much larger mistake down the line. The servos aren't perfect and each of them had their own variability, which means that the globe doesn't spin cleanly. Now these two problems could be solved by using smaller servos and then shrinking the base as a result, and therefore using smaller links for the fingers. But the servos would likely be weaker, and this leads me to my final problem. I posted this short around this time of the project, and I got a few comments about how this kind of looks like a leaper from Arc Raiders. And fair enough, when I turn it upside down, it kind of does. But the weight is too much for the motors because the fingers are too long. It can stand here on its own power, but it's definitely not steady. And I can even smell the motors getting hot too. Doing some quick maths, each of the servos for the links of the fingers can only output 1 kilogram of force if the servo is 90 degrees away from the ground. If I made each of the links shorter, maybe by about 25%, then it would be easily able to handle its own weight, and each of the fingers would probably be more accurate too. But that wasn't in the original design requirement, so whatever, that can be in the next project. I put the CAD files in code on my Patreon if you want to build your own Evil Desk ornament. I've already uploaded a teardown video so you can see how all the parts come together in detail. An Arc Raiders Leaper will likely be my next project, but comment down below what you think I should build next. And remember, subscribe for robots! Thanks for watching.